Olivier Goffart from Wobok, who's here to talk to you first thing in the morning about lock-free programming. Please give him a big round of applause.
Thank you. So I will start by presenting myself. I'm from Belgium, French-speaking part, so I apologize for my French accent. It's really hard to get rid of. I used to work in Trolltech. Before that, I was a KDD contributor, so I came from KDD, then I worked for Trolltech, and then Nokia. I worked on many areas of Qt within, while still working for Qt, and currently I'm still the maintainer of Mock. In 2011, I left Nokia to start a company called Wobok. We're offering services around Qt. Check out the website. We also have a C++ code browser. If you wish to browse the source code of Qt, you can just go to code.wobok.org and enjoy nice code browsing, just like in IDE. So the goal of this presentation is to introduce you to lock-free programming and to the Atomic API. It's really an introduction, so after this talk, you would not be expected to be doing real lock-free programming. My goal is to interest you to this topic, and maybe you will research even more and try to do your own lock-free programming, but in practice, it's not going to be so useful. But still, I think it's really useful to know for just the general knowledge and to improve your programming skills. And with the current trends of CPU getting more and more parallel, we might see lock-free programming more used in the future. So let's start with a simple example here. So we have this Singleton pattern. I guess you're familiar with this pattern. I forgot to mention that if you have any question at any moment of the talk, just raise your hand and I try to answer it. So the Singleton pattern is just you want to have one single object that you might use many times in your application, but you only want to have one instance. And in this case, we want to have it initialized on the first use. So the application is going to call this instance function, and we want it to be thread safe, so we added a mutex around the whole thing, and on the first use, if it's not yet initialized, so this is a static variable, if it's not yet initialized, we're going to initialize it. So right there, everything is still, probably you've seen this pattern before, if I'm not mistaken. So then someone might think, oh, but there we have a mutex, maybe it's slow, maybe because we are going to lock every time we want to access this singleton, we're going to lock this mutex. Maybe we can be more optimal and remove the mutex for and only lock if we're going to actually initialize the singleton, but every subsequent run, then we don't need to lock. So in that case, if two threads are trying to initialize the singleton at the same time, they both will see that the instance here has not been yet initialized. So they both try to acquire the lock, but only one will instantiate the singleton because the other one will see that it's already initialized. However, I've wrote on the slide that it's wrong. Do you know why? Can you guess what's wrong with this example? Yes? So the answer that was given to me is that this might not be atomic, and therefore no. This one? Yes. This might not be atomic, and so maybe we can see half like maybe the bits are only half set and it points to something else in memory. Yes, but that's normally, well, that could be an explanation. But what is even more a problem is that we might use the singleton before it's fully initialized. So this line number 6 here, what does it do? This new operator will first allocate memory, then call the constructor, which will initialize the singleton. This can be maybe some lookup table or some pointer to initialize. And then S instance will be set. That's if everything goes according to what we see. But as you might know, the compiler can optimize and reorder things. So maybe the compiler can say, okay, I already have the address after the new. I can already assign to S instance right after the new, and then I will do what my singleton does. Maybe that's going to be in line. Then the compiler will see I can just set S instance and then initialize the singleton, which means another thread comes and see that S instance has been set, and then it's going to use the singleton before it's initialized. That's the main issue. So how do we fix this problem then? We want to avoid the compiler to optimize. One way could be to use volatile, but volatile is not enough. Volatile is meant to be used for hardware register. It's not meant to be used for trading, so I'm not going to mention volatile ever again in this talk, because volatile just avoids the compiler to optimizing. But it's not only the compiler that reorders, it's also the CPU itself. If you think of the model of a CPU which reads one instruction, load or do the thing, and then read the next one and do the things, it's not the case anymore in modern CPU. Modern CPUs have large buffers where they load many instructions they're going to run, they see in the future. They try to compute all the dependencies between all the instructions and try to order the instructions in the best way to fill most of the pipeline and to do a lot of operations in parallel. You have to know that reading from memory is really slow because there is so many levels of cache, and if there is cache misses, you have to wait hundreds of cycles for the read to be complete. So what happens is that the CPU sees that you might do a read long in the future, so it will already tell the cache to load the memory before you need it. So, but maybe because of that, then everything can be reorganized. So back to the previous slides. Even if the compiler will make sure that the constructor of the singleton is called before we initialize the S instance, maybe because of the buffers or the reordering, what will happen to the memory is that the second thread will see S instance as already initialized, but as already set, but the singleton is not yet initialized, and then we're going to use a singleton that was not initialized, and that's bad. Yes, so how do we fix this? The magic thing I was going to talk about is here I've added a QAtomic pointer. So we fix this by adding memory barrier. Memory barriers are a way to tell the CPU, hold on, I don't want you to reorder my code here because I know that there might be other threads, so you have to do everything, or you have to do those operations in the order I tell you to do so. So before it was just a pointer to a singleton, and now it's an atomic pointer to a singleton. And we say load acquire here, and when we are going to set it, we're going to say store release. And those two put the memory barrier. So store release says that this has to be done, that this has to be done after the singleton has been initialized. So we make sure that everything that was before this store release is done. And the load acquire means that all the reads that are going to happen, after we call this function, like all the reads to the singleton, really appear after we did the load. So if we see that the load was initialized, all the read has to be done after the constructor was called. Oops, didn't. Yes, so the acquire and release barrier, they all goes together, and they really mean that this code, the initialization of the singleton, will happen before the code that happens there. So this actually defines and happens before relationship, that is the wording in the C++ standard, which I'm going to come to later. But this is a lot of code to write, and so the best solution to implement the singleton, I will say, is this one, much shorter, and this, according to the C++11 standard, is thread safe, because the C++11 standard specify that the function static objects have to be initialized and first used in a thread safe way. In addition, it's even going to be destroyed when you quit your application, which was not the case in the previous example. Yes, but this is only in C++11, so if you don't use C++11, you might want to write this. Or we also have a macro in Qt called QGlobalStatic, which use this pattern if a C++11 is there, or this pattern if it's not. Yes. So let's talk a bit more about C++11 and the memory model. In the previous standard, C++98, there was no mentions of threads whatsoever in the standard. So the compiler was allowed to do any optimization that, as long as it looks like that's what you want to do, if there is only one thread. For example, if you want to write 1 byte of memory, the compiler could decide, oh, I can read 64 bytes in my register, modify 1 byte, and write 64 bits in the register, or 64 bytes, and you might overwrite values that are used by another thread while you don't want to. The compiler can even take stuff outside of the lock, like if there is a loop and you're locking inside the loop, then maybe it sees, oh, I don't want to read all those values all the time, I will read it before the loop, and then write it after the loop, but then you write or read outside of the lock, which is also not good. So there was, of course, in practice, people were doing multi-threading in C++ before C++11 came, so compilers were still trying not to do too much optimization that were breaking with threads. But there was still fights between, for example, there was a famous fight between Linus Torvalds and the GCC developers on such items. But that was C, not C++, but same problem. But the C++11, are you already using C++11? Raise your hand, those who are. Very good. So you might have heard about all those nice features like auto, lambda, and such, which are indeed nice, but one feature that is less talked about is the new memory model. C++11 define race condition. In C++11, it's acknowledged that people use thread, and it restricts the optimization that can be done knowing that there is thread. For example, the C++ standard says that you are not allowed, or that the compiler is not allowed to write a value that wouldn't be written otherwise by the code. And we also have some standard library support for threading. Yeah, so I've just put here the definition of our race condition. It's in the chapter 1.10 of C++11, 21st paragraph. So there is at least 20 paragraphs before that defines things like happens before and such. So the execution of a program contains a data race if it contains two conflicting actions in different threads, at least one of which is not atomic and neither happens before the other. So we will see that when you have a mutex, the critical section of a mutex is defined as happening before another critical section of a mutex in another thread that happens after. So in that case, you can write on the same memory location if you're inside a mutex. You can also write on the same memory location if both are atomic. But you cannot write on the memory location if you don't have those barriers. So if you have a Boolean, for example, bool quit, and in your thread you loop and you check the value of quit, and in the other thread you say quit equals true when you want to stop your computation. Well, that's not valid. That's a undefined behavior unless it's an atomic variable or you do it inside a mutex. Okay, so up to now the singleton was still locking, there was still a mutex. So let's get into the subject and talk about lock-free programming. And lock-free programming is really programming without any mutexes, without any lock. So that's also no spin lock, because a spin lock is a lock, even if it's not a mutex. But what's wrong with mutexes? What's the problem with mutex? It's slow. Yeah. So usually mutex are fine, even though we might think they're slow, and they are, but they are probably less slow than what we might think. But still, they're indeed slow, especially if there is contention. So that means that there is a lot of threads trying to access the same mutex at the same time. Imagine one of the threads locks the mutex, but then goes to sleep. It is scheduled away by the operating system. Then all the other threads are going to reach this time when they have to lock, and all the other threads are also going to be descheduled. That makes a lot of waste of CPU because of all the context switch that the operating system will have to do. And also the CPU will be underused because only one thread will be able to run while all the other cores are sleeping. If you do real-time application, there is a whole set of new problems like priority inversion. That's if you have a slow thread with low priority which acquire the mutex, but then a very fast thread with very high priority wants to lock this mutex but is blocked and have to wait for the slow thread to finish with its critical session with its low priority, and maybe there is medium priority thread in between that are taking the CPU while the very important one has to wait. If you have interrupt handler, what happens here? You have your main process, which is going to be interrupted to run the interrupt handler. Of course, you cannot use mutexes here because if your main process has acquired the lock, because it's not running anymore when the interrupt handler is running, it will never unlock it, and you will not be able to acquire it inside the interrupt handler. And convoying is the fact that all the threads are probably doing the same operation, so they're taking the same time without the lock and the same time with the lock, and they're all going to reach the critical section at the same time, and then they're all going to block on the critical section, and then they're all going to do their computation and reach again the critical section at the same time, and that's not as efficient as we would like it to be. So that's why lock-free programming are sometimes faster. So we would like them to be faster. That's why we write them. But we need to be very careful because actually this is not always the case. So we really need to profile the application before to be sure that it's because of the log contention that it's slow. And we also need, after we did it, we again need to profile to see if what we did is really faster. The good point is that there is no risks of deadlock because there is no lock. And that's very useful if you want to be robust against crashes of another process. So imagine you have some shared memory across process. You want to keep the data in a consistent state, so they will work on this data. So one way would be to have locks. But if one of the processes is killed while holding a lock, then all the other ones are going to wait forever for this lock, and that's not good. But if there is no locking, then you're safe and you're robust against any thread or any process being killed. There is a function in Qt called QtDD14 which should not really be used because even Qt does use lock, and if you terminate a thread while it's locking, while it's having a mutex, you are going to be in trouble. And also lock-free algorithms are more difficult to design and understand. You really need to think what can happen between each instruction, or even while a single line of code is running, things can happen in other threads, so you can never be sure of what happens. So that makes the whole algorithm way more difficult to reason about. But this is also a bit fun. So that's, but still. So that's why I'm presenting to you. But still, it's also going to be more difficult, and this is why you should really think twice about trying to do lock-free algorithm. So this is a question over there.
The risk of deadlock when the thread crashes. Does it still exist if you use a mutex log?
Yes, because when the thread is terminated, it's not an exception or anything. It just terminates the threads, stop anything, so it won't unlock the mutex. Yes. So the question was whether or not there will still be a problem if we use the QMutex locker and we try to terminate a thread. So yes, those are our weapons for log-free programming. It's the QAtomic APIs. So all the functions can be mix and match with what we are going to do, and some memory ordering. So you have, for example, test and set. You have test and set acquire, test and set release, test and set ordered, and such. Let's go and describe the more important functions here. Fetch and store is the equivalent of a swap. So I want to swap the old value with a new value and return the old value. So this is basically doing what's written there. I take the old value, then I assign the new value, and I return the old value. Of course, if it was implemented like that, that wouldn't be atomic, because between the line 3 and 4 here, the thread could come and modify the value, and you would then erase the value that was just set by another thread, and you don't want that. You really want to swap it without losing the values. So this has to be implemented in assembly. The Atomic API is one of the only part of Qt that has its own assembly for each supported platform. Fortunately now with C++11 we can implement it on top of std::atomic. But still the support of std::atomic, even in the compiler that supports it, are not as good as the one we had in Qt. So even GCC always used a full barrier when we do not. When we say acquire, we only put an acquire barrier, while GCC always used a full barrier. But this hopefully will be fixed in the future in GCC, so we will be able to use std::atomic in many more cases. Fetch and add allows you to add a value atomically or subtract because you can use a negative value here. Yes, again, this line here is not a single operation. It reads the value from memory to a register, increment this register, and then write this register to the memory. So this is reads, modify, write, and that is not atomic. So again, this is really important that this is done with an atomic operation and not just like that written in the code. And last but not least, test and set. It's some other API, or in some books you will read it as called compare and swap. Test and set, you want to change the value of your atomic, but only if it has the expected value. So you want to basically set the value only if it has the expected value, and if this fails, it will return false. And if it succeeds, it will return true. So we will see how to use that in a moment. But first, let's explain a bit more about memory ordering. So we've seen that we want to add memory barriers so the CPU do not reorder. But we don't want to add too many barriers because we still want the CPU to do its best. Because if we had too strong barrier, then we limit the capacity of the CPU to be fast, and we still want the CPU to be fast. So we have the acquire and release barrier. They go in pair. Imagine the name comes from the mutex way of doing things. So imagine you have a mutex. First you acquire the mutex, and then you have your critical section, and then you release the mutex. You do not want that any of the operations done inside the critical section, so between the acquire and the release, are done outside of the critical section. So you do not want anything done inside the mutex to be done either before the lock or after the lock. So the lock will put an acquire barrier, so any memory access following the atomic operation that is acquire might not be reordered before the operation. So any operation that is done after the lock will not be reordered before the lock. That's what it means. Release is when you release, any operation that is done inside the lock or before the release will not be done after the lock has been done. So the lock really says everything that has been done now is done. Usually there is always in your code you will always see a release matching an acquire. If you want to be more strict and also more safe, you can use the ordered memory barrier that says, I don't want any reordering around this memory operation. And the relaxed is more like, I just want this operation to be done atomically, but I don't care if you reorder my code around or not. So now we can use the test and set operation here to implement our singleton in a lock-free way. Totally lock-free without any mutexes. So the way it works, if two threads are coming in the same time for the first time as before, we're going to make a load acquire there just like in the previous way. And they're going to both create the singleton. And then they're going to try to set it to the static instance. So we want to set it from 0. So if the first one will manage to change from 0 to its new singleton, so that will work. That will return true, and then we will continue. But in the case that it failed because it was not 0, because another thread came before and set the singleton, then this will fail, and then we'll be like, oh, we've created this singleton for nothing. Now we'll have to destroy it. So we delete the singleton here, and then we reload the one that was written by the other thread. Yes, so you might ask yourself, is that really faster than doing a lock? And I will answer probably not. If you have 10 threads coming at the same time, 10 threads are going to construct a singleton, and then 9 of them are going to destroy it afterwards. That's a lot of useless computation, where you could just have locked and wait and let maybe some other process take the CPU. So in that case, it's probably not worth implementing it that way. I'm just putting it there because there are cases where this pattern might be useful. And case, for example, instantiating the singleton might be really fast, and releasing it might be really fast if you have a specialized allocator and you need to do that a lot. So not for a singleton, but for maybe nodes inside other structures. Then you might have this case where creating one and, oh, I didn't need to create one after all, and releasing it might be better than blocking. Okay. So is there any question about what we've seen so far? Because we're going now to start working on a really log-free data structure, which is a log-free stack. So the stack is implemented as a linked list, where we have a head pointer that points to the top node of the stack, and each node points to the next one. So when we want to push a node, we're going to have this node C that we want to push. We'll set the next pointer of the node that we want to push to the current head, and then we will try to atomically change the head from B to C. It's important that it's atomic, because imagine if you have 2 threads, they both want to push a node in the list. So both of them are going to atomically change here head from B to their node. In that case, the thread 2 succeeded, and if we just were now to change head to C, that we would leak the D. But what happens here is that the atomic operation fails, the test and set fails, so it returns false, and we can try again. And we try again with a new head now. So here is the code. So we have a loop, and in the loop we set the next of our nodes, and then we're going to atomically change from this value. So this node here is owned in a way by the thread. So we know that n.next or n next here is local to the thread and won't be changed by other threads. But heads here might be changed at any point. So we really want to atomically change from the previous node to yeah. So we really need to check that it's still the previous head is still there. So the n.next that we've read here, that was the previous head, and we want to change from the previous head to the new node. Question?
Why does it have to be test and set ordered instead of test and set release?
Good question. So I put test and set order because I just wanted to be sure. But it is true that then you have to question what would the memory ordering of this operation need to be. And this actually depends on what you do with your list. Usually when you put something into a linked list, is because you want to publish the linked list or you want to publish this node to the other threads. And in that case, so the thread has made something with a node, has initialized some variable inside the node, and so you want to publish this. So in that case, indeed, that would need to be a release. I'm trying to think cases where you would like to have an acquire when you push, and no, I cannot think of cases, but it really depends on what you have to do with your list. But it's true that in most cases, pushing to a list will be a release rather than an ordered. So is this really faster than looking? Because one might think, oh, but this might loop forever. Is that not a problem, that it's not bounded, that if other threads are doing things, this will loop forever? And that's something that is not so intuitive, but the fact that this test and set operation will only fail if other threads have done something. So that means that if this fails and we have to loop, that's because there was progress, there was general progress of the whole algorithm, of the whole computation, because other threads have made progress. So it's okay for a single thread to loop because the whole application is making more progress. Well, if you have to lock, you can also lock for a long time, but maybe the thread that has the mutex hold is not doing any work because it's also not having the CPU at this time. So, is there any more question about the push? Yes?
On single-core machines, probably just they're not using the whole time slice until it's all disrupted. So I guess it only works nice for multi-cores.
On single-core machines, you will probably not loop then. So, but on the other hand, you might lock the mutex and then be descheduled, and then other thread comes and are blocked. So it's even more efficient on single core machines here. Yes. So the pop is a bit more tricky. So what we want to do here is to pop the node B, so to take the node B and then change head. We can just change head from B to A. That was quite easy, but unfortunately this is not correct. But let's first see this algorithm and then see why it's wrong. So we take the node N in a local pointer that is the node that we're going to return. We load this node and we try to atomically change from this node to the next of this node. If the node is null, we just return null, like there is nothing on the list. Again, I could have used acquire here, but I could have used acquired in the test and set, but that's not what's wrong when I say it's wrong. There is actually two things that might go wrong here with the pop. The first one is that we read the current head that points to a node, but then right after we've read it, other threads come and pop the node and maybe delete the node, destroy the node because they've finished with it. But here we're going to call n arrow next, so we want to access the node even though maybe the node has already been destroyed. So that's the first problem. And well, what's the solution for this problem? Is just not to destroy the node. So that means that usually in log-free programming, not going to destroy the node, but you're going to put them into some queue to reuse them later, because you wanna be able to access some data of the node, even though this will fail if the operation will fail if the node is no longer on the list, but you still want to access it even if you won't use it really, because the operation will fail. So we want to make sure that the memory has not been freed. And so that was the first problem that was easy to fix. But then there is the second problem, which is called the ABA problem. So let's imagine we have the thread 1, which wants to pop the node A here. So we have this pointer to this end pointer to the node we want to pop, and we're going to try to atomically change from A to B. But then thread 2 comes and pops the node. Here everything is fine still, because if thread 1 would resume, the atomic operation will fail, because we want to change from A to B. But thread 2 continues, or maybe another thread 3, and pops the node C on the list. So then what will the problem be? Again, if the thread 1 resumes now, there will not be any problem, because it's want to change from A to B, and so the atomic operation will fail. But thread 2 hasn't finished running, so maybe what will happen is that maybe thread 2 destroy the nodes and take it back and put A back on the list, or back on the stack. And now do we have a problem? So we want to change head from A to B, and indeed we have, because the atomic operation will succeed, and we will pop A, but we will also forget about C. So that's the ABA problem, and it's called like this because you have a value A, and then it changed to another value, but then it becomes back the same values, and all the invariants you had before are no longer valid. So how can we solve this problem? The easier solution is to add a serial number in addition to the data you want to change. So for pointers it's a bit hard, because you only have like 64 bits of your pointer to change, and you don't have many more bits. But it works better. Instead of working with pointer, you can work with indexes in array, and have half of the bits for the index of the array and half of the bits for a serial number that is incremented, and therefore you don't have this problem of ABA problem. Hazard pointer is some kind of interesting algorithm in which each thread publishes the pointer it's about to read. Therefore, before deleting the node, the thread that wants to delete the node will look at each thread if it's about to read one of those pointers, and will not try to destroy the node if this is the case. If you have a garbage collector, so that means that if the thread that wants to read the node has still a reference to the node, you're also safe, because the node will not be destroyed and reused as long as one of the thread has a reference to it. This is so in C++ you don't have garbage collector, but you can use reference count for that. Yep. Any questions so far? So you might ask, where is where is this kind of programming used in Qt, and I have put here some example of where Qt uses log-free programming. We use that for the reference counting of any of our shared data structure. For example, QString, QByteArray, QVector, any of the shared class, there we reference count them, and we do that in an atomic way without mutexes, in a thread safe way. QMutex itself cannot lock, of course, because it does lock, but all the code that is managing the QMutex cannot lock because it's managing the QMutex. So we want to implement a mutex. So we need to be log free for all the parts before we lock. QMutex is actually quite interesting because if you don't have contention, it's going to be really fast because it's only one. To lock a mutex is only switching from non-locked to lock, and to unlock is only switching from unlocked to lock, from locked to unlocked atomically. And if this succeeds, then there is no need to go into the operating system or anything. It all happens in user space as long as there is no contention, as long as there is only one thread trying to access the mutex. QGlobal static, as we saw before, uses this atomic if you don't support C++11 to thread safely initialize your singletons. QTimer, or rather QObject, uses a quite complex log-free data structure to allocate timer IDs. So when you do start timer, it needs to create a new timer ID, and we do that in a log-free way. And there is some other uses of log-free programming to manage, like the event loops when it has to stop, QThreads. There are some Qt concurrents. There is a lot of atomic in Qt concurrent as well. Other examples of use of log-free programming is RCU. That stands for read, copy, update. It's a pattern in which there is only one thread that modifies the data and all the other threads are reading. And in order to modify the data, we first copy the data. While we read it, we copy it to some other locations, and then we atomically change the pointer to the data. Multiple word compare and swap is some ways to implement. If you have many pointers that you atomically want to change all of them from one, with a compare and swap from one set of pointers to another set of pointers, you can do that. The way this works is because you assume that your pointer points to data that is aligned, so you always have a few bits free. And so so you can use this bit to say if the least significant bit is 0, then you have a pointer to your data. If it's 1, then it's a pointer to a special descriptor which is going to contain the operation that we want to do, and therefore for the other threads that come and wants to read this pointer will see, oh, this is not a pointer to my data, it's a pointer to the descriptor, and each thread will help each other to finish the operations. We can use multiple word compare and swap to implement transactional memory. So transactional memory here, for example, we can implement the pop like this. So this transaction atomic will be a macro that do the looping. Head will be some special smart pointer to some transactional atomically safe data structure. Same for the next node. So what does this do? That we record that we've read from head, we've record that we've read from head next, and we've record that we write to head, and then when the loop, but we don't do anything yet, and when the the loop is over here, or then we try to atomically do that. And if this fails, we try again. So there is software transactional memory, or even most recent CPU have even hardware transactional memory that can do that in hardware. And this might even be in C++17 because there is a proposition to add that inside the C++ standard. Any questions? So as a conclusion, I will say that you might still use mutex. I don't want to say that this was wholly useless, and I hope it was still interesting, but that in the real world it's so much easier to use mutexes, and especially you really need to profile and make sure that you really you don't want to micro-optimize. So that's the end.
Yeah. So we have some time for questions now. Please put your hand up and let me get to you to give you the microphone before you ask the question. Otherwise, it doesn't get recorded. And it's going to be a little challenging. I might have to pass it along the rows.
If you do an acquire or ordered operation with atomics, how far does the is the memory or reordering inhibited? Like how far ahead?
So it's only inhibited for the operation you do it for. So when you do an acquire, it's any operation after forever will not be put before. So that also means that when you have acquire and release in a mutex, what's done after your mutex, even if it's done after, will not be put on before.
Yeah, I understand.
Hi. What do you think about this QRead-write lock in this context? There's a read-write locker, and I sometimes use it instead of a mutex.
Mm-hmm. Yes. Yes. So the QRead-write lock is also a lock, because if there is one writer, then all the reader will have to stop as well. The read-write locker is also very useful to avoid contention if you have a lot of reads and not so many writes. So I would recommend to use it, even though, again, you might want to profile because QMutex is more optimized than QRead-write locker currently, but that might change. But yes, so this is the read-write locker is really useful to avoid contention if you have not so many writes.
Anything else? Okay. Well, we have another round of applause. Thank you for an excellent talk from Olivier.
Thank you.